So section 9.6 transitions with restocking and culling. I think this first paragraph does a really good job of explaining what this is all about, and then I'll speak about the example. In all the transition situations we've dealt with so far, the total number of things involved, shoppers, birds, trucks, etc., has remained the same throughout each transition. We're now going to look at a transition where things are either added or taken away. When we add something to the situation, it's called restocking, and when we're taking away something, it's called culling. So the restocking and culling matrix is often defined, or is defined as this plus B part. So the status that we're after is equal to the transition matrix multiplied by what the status was immediately before this status. So in this way it's defined as being Sn plus B, where B is the restocking and culling matrix. Please notice that we need to do these in set steps. At no stage can we involve a transition matrix being raised to the power of something. Alright, so if we're after, as an example, the status after 10 weeks, we can't just go t to the power of 10 multiplied by S0 plus some matrix B. Alright, we can't do it that way. We have to do it step by step, always, whenever you've got this plus B taking place. Alright, let's look at this situation where we've got ourselves a commercial fish breeding farm. Now, in this farm, we have got eggs, babies, adult, and dead fish. So that's the status moving to this. So from and to. So remember, eggs, babies, adults, and dead. Now, it makes sense, doesn't it, with this D column? So once a fish is dead, it's always going to remain dead. And you'll also notice that we've got zeros in the top part of the matrix because basically eggs aren't going to remain eggs, but 30% will move to being babies, 70% will die. With our babies, then we're not going to go backwards to become eggs, and we're not going to remain as babies, but 35% will go on to become adults, and 65% will die. With our adult fish, 60% will remain adult fish and 40% will die, and then of course 100% of all dead fish will remain dead. Now, we are told that the company removes 500 adult fish, so they take those out of the pondage and sell them off. They add 200 babies, and they add 8,000 extra eggs as well, or 8,000 eggs are produced by the adults who are laying them. So there's an extra 8,000 eggs that go in to the pondage. There's 200 babies which are added into the pondage, and 500 go out. Now, initially when we begin this, we know that there are 20,000 eggs, there are 4,000 babies, there's 500 adults, and there are no dead fish. We've got this S of n plus 1 matrix is equal to the transition matrix, which is this, multiplied by the status immediately before it, so we denote that as being Sn. So the status immediately before S of n plus 1 is Sn, plus the culling restocking matrix. And our first job is to define this culling restocking. So 8,000 are added, we write that as positive 8,000. So there's 8,000 eggs which are added to it. There are 200 babies which are added. We take out 500 adults to sell to restaurants, so that's minus 500. And at no stage are we adding any deads there at all, so we just leave that as being 0. Find the number of adult whiting after 1 year. So we've got S of 1 equals the transition matrix multiplied by S0, the status of what we had immediately before, plus the culling restocking matrix. And if we do that calculation on our CAS, you'll come up with this matrix. We are after the number of adult, so that's eggs, babies, and adults. So you can see there are 1,200 adults after 1 year. Find the number of adults after 2 years. So here we're after S2. So it's the transition multiplied by the status immediately before, which is S1, and S1 has been found in part B, so that there is the S1, plus the culling / restocking matrix. So here's my transition matrix right from the beginning. There's the status after 1 year, that's found here. Here's my culling restocking matrix, and that's what my status will be after 2 years. So adult whiting, eggs, babies, adults. So you can see there are 2,390 adults after 2 years. Now, instead of removing just 500 adults after the second year, the company decides to remove enough so that the number of adult whiting remains the same it was at the very start. How many do they remove? So at the start, S0, there were 500 adult whiting. After 2 years, there were 2,390 adult whiting. The difference between that is 1,890. So after 2 years, to return the adults back to what it initially was, i.e. 500 whiting, then they need to take out 1,890 adult whiting. So we're looking at part E of the question. The company decides to start another farm under exactly the same circumstances, but with one change. The breeders realise that the number of eggs laid by the adult whiting during each year depends on how many female adult whiting they had each year. They come up with the following modified recurrence relation where they estimate 50% of the adults, i.e. females, each lay 200 eggs a year. So here's our recurrence relation involving matrices. So S of n plus 1 equals the transition matrix, which is the same transition matrix as we had previously, multiplied by Sn, which is the status immediately before the one that we're after, plus this slightly new culling restocking matrix. So notice that we're not adding 8,000 eggs, we're just adding 0 eggs here. Plus, we've got this particular 4x4 matrix multiplied by the status immediately before the one that we're after. Also, what's given to us is the initial status S0, where we've got 20,000 eggs, 4,000 babies, 500 adults, and 0 dead. We need to work out how many eggs there will be after 1 year. So we're after S1, so it's going to be the transition matrix multiplied by the status immediately before the one that we're after. So in our case, we're after S1, so it's S0, plus that culling restocking matrix, plus this particular 4x4 matrix multiplied by S0, the status before S1. There's my transition matrix. Here's S0. Here's the new culling restocking matrix. That's the new part of my recurrence relation for this particular farm, where it's the 4x4 multiplied by S0. And we come up with this matrix here, the status after 1 year. So 50,000 eggs, 6,200 babies, 1,200 adult, and 16,800 dead. And so from that, we can see that there will be 50,000 eggs after 1 year. Now, how was it that they come up with this matrix times that matrix and realize that that would work given this situation here? Well, what we're talking about in the question is that 50% of the adults will lay 200 eggs each. Now, given that initially there are 500 adults, 50% of that would represent 250. So there's 250 adults, and they each lay 200 eggs. So what we've got going on there is 200 times that 250 to give us the 50,000. But why does that times this work out to be the 50,000? So this shows the same kind of calculation, or exactly the same calculation. There it all is there. But let's just look at the last part. Why is it that this matrix times that matrix will produce 50,000 eggs? You can see that this times that plus that gives us zeros for the eggs, and the 50,000 is obviously achieved by taking this 4x4 multiplied by S0. This is a 4 by 4 being multiplied by a 4 by 1 matrix. The two inners are both 4s, so the multiplication is possible. And then the dimensions, or the values on the outside of this, is a 4 and a 1, so our answer matrix will be a 4 by 1 matrix. This 50,000 is found, or is in the position 1, 1. It's found by taking the first row by the first column. So 0 times 20,000 plus 0 times 4,000 plus 100 times 500 plus 0 times 0. So you can see there that the only real calculation that's going to add anything to it is the 100 times 500, which gives us that 50,000 that we're after. So it does make sense that we have our S0 being pre-multiplied by this particular matrix, because that will give us the 50,000 that we need of eggs that are thrown into the pondage. Of course, as I said before, that last part, understanding how that times that produces the 50,000 isn't really crucial, but given this recurrence relation, you need to be able to throw in all the variable bits of information to work out that we have 50,000 eggs.